Hi, my name is Don Batory. I'm an associate professor in the Department of Computer Sciences at the University of Texas at Austin. I'd like to bring you up to date on Genesis. Genesis is a continuing experiment in database management system extensibility. Our goal was to demonstrate that it was possible to build customized database management systems literally in minutes by composing prefabricated components together. Genesis is also an experiment in large-scale software reuse. It has been cited as one of the largest examples of large-scale reuse that's ever been achieved in a university environment. And it's also an experiment in an open system architecture to design. Virtually all the techniques that we have used to build Genesis and to design it have absolutely nothing to do with database management systems. The techniques can be applied to many domains that have no database management content in them. What I'd like to do is to review this design framework, and you'll see that it's deceptively simple. What I'll do is to review some of the framework concepts and then illustrate these concepts using Genesis. In designing an open system architecture, one has to identify realms or sets of components that have exactly the same interface. Here are two realms, R and S. Think of a realm as an enumerated type. Well, realm R, or enumerated type R, contains three components, A, B, and C. Realm S also contains three components, D, E, and F. And some of these components can have parameters. For example, all components of S have a single parameter, which is of type R. You can think of components as parameterized types. But what's important here is that each one of these components has exactly the same interface, which means that they are plug compatible and they're interchangeable. A software system in this universe is a type expression. Again, referring to these realms R and S, System 1 is a composition of component D with component B. System 2 is a composition of component D with component C. And System 3 is a composition of component F with component C. These components in both of these realms, or in all realms, turn out to be primitive units of programming for that particular domain. Component reuse in this universe is pretty obvious. Different systems or different expressions that reference the same component mean that that component is being reused. Here are the three systems that we saw in the last slide. We see the component D appears in two different systems or two different type expressions. It is being reused. The same for component C. One of the unique and most important features of our framework is the identification of reflexive components. These are components that literally can be composed in virtually arbitrary orders. Or, in terms of our formalism, components of some realm T that have parameters of type T. Here's an example realm T, which has two components, M and N. Both of these components have a single parameter of type T, which means that they're reflexive. Again, reflexive components can be composed in arbitrary orders, which means that M can sit on top of N, and also N can sit on top of M. Now, this seems to be very odd that the interface to a component is exactly its abstract interface equals its concrete interface, but some of you have already seen some of these ideas. They're called Unix file filters. Whenever the output of one process is piped into the input of another, you're composing reflexive components, where each reflexive component turns out to be a process. An open system architecture is specified by a set of realms with interchangeable components. and 2 rules that define legal compositions of components. Genesis itself supports over 9 different realms. That includes data languages, link implementations, file structures, and so on. We'll take a look at these very shortly. The other aspect to enforce design rules is a graphical layout editor for composing components. This layout editor enforces design rules for component composition to ensure that any system we design will in fact work. Now, I'd like to give you a demonstration of Genesis. What I want to do is overview some of the realms and some of the components that we've implemented. Next, I want to use the layout editor to specify customized database management systems, or a single system, that would be implemented on over 30,000 lines of code. We'll instantaneously build this prototype and then run this prototype on a demonstration database. All of this is going to occur in approximately 10 minutes. Okay, let's take a look at the layout editor. This is the Genesis layout editor. Here is the Genesis library, or the date library. Here are the realms that I mentioned before. And these are the 9 realms in Genesis that happen to have more than one component. The data model or data language realm, we're currently supporting 2 different components, QUEL and SQL. Links are different implementations of relationships between 2 different relations. There's merge join, or standard link algorithms. These are join algorithms, or the more traditional ring list and pointer array for physical connections between tuples of different relations. Again, one of the properties of realms is that all the components have exactly the same interface. So all these components have the same interface, and they are plug compatible and interchangeable. File mapping is a realm of reflexive components, which includes indexing, data compression, transposition, client-server components. When we're processing operations using a query processor, we need stream operations, such as sort, cross-product. L-filter is a special stream operation that's used to process cyclic queries. We support an array of file structures that includes non-keyed heap structures, single-keyed hash and B+ trees, and multi-key grid files. We also support page-based recovery algorithms such as shadowing, before image. If you want no recovery, that's a possibility. And in a future version, we will have DB cache. And finally, we have a set of basic types. These are the primitive types that one can reference in database schemas. Now, all of these realms are extensible. One can add components as is needed. So let's fire up the Genesis layout editor called Date. Date has an extensive array of help displays, one of which is on architectures. The basic design concept of Date is an architecture or subsystem, which is a directed graph. Nodes represent components or building blocks, and edges represent communication paths. The most primitive architectures or subsystems are file structures. They map internal relations to disk. A storage system maps conceptual relations to their internal relation counterparts, which are then stored on disk via file structures. Networks build upon file structures, storage systems. Networks allow links to interconnect different conceptual relations together. A relational architecture, or subsystem, is a high-level data language that sits on top of a network. Object-oriented architectures, not shown here, but what we are implementing now, are sequences of components that sit on top of relational architectures. Now let me show you the relational architecture of Ingress, just to give you an idea of how we represent database designs. University Ingress presented Quell as its data language. It mapped from a non-procedural front end to a procedural interface where files and links were exposed. Links were implemented by nested loop algorithms, and files or conceptual relations were stored by the Ingress storage system, whose design is this. This storage system maps relations, conceptual relations, to inverted files. So if we pull up an information on index, the index component accomplished most of this mapping. It mapped a conceptual relation to inverted files. Here's where you plug in the data file implementations. Here's where you plug in the implementation of the index files. Again, think of index as a parameterized type. And in fact, think of all components as parameterized types. Now, if you recall, University Ingress allowed database administrators to store data and index files as ISAM, heap, and hash structures. Date captures this multiplicity of implementations by a powerful concept called a software bus, which is shown by a scrollable window right here. The software buses for the data and index parameters contain the file structure architectures ISAM, heap, and hash. Let's take a look at the ISAM architecture or subsystem. The ISAM component maps an internal relation to a set of logical blocks, some containing data records, others containing index records. In this particular architecture, the data nodes are implemented by the unordered primary unshared component. As an example, a logical block here consists of records R1 through R8. And this particular component maps these records onto a primary block and a string of overflow blocks. And finally, the actual storage of records in blocks itself is handled by the fixed architecture, or fixed anchored building block. Here is our header, and here are these slots, fixed length slots of R+1 bytes. The extra byte is needed to indicate whether the slot is fixed. Now, what we've just done is surveyed the architecture of University Ingress from its data language level all the way down to the way we arrange bytes on blocks. And so the basic idea is that we're capturing an enormous amount of detail very quickly and very compactly. Now let's go and build a version of DB2. DB2 starts out with an implementation of mapping conceptual files or relations to inverted files, just as Ingress did. In DB2, index files are stored in a B-plus tree structure. So we go and select File Structure. Here's the list of all file structures that we can use to implement that index. We select B-tree. Now, instead of storing records directly into a heap, what we can do is we can modify the architecture slightly by compressing it. So we go and select a file module or a component, and we go and select run length encoding. And now we go and store that in a heap file structure. So again, we click, we select on the file structure, and the legal file structures are listed here, so we select heap. Again, what this storage system does, it maps conceptual relations to inverted files, where index files are stored in B-plus trees, data records are first encoded by run length encoding, and then stored in a heap. Let's go and save this definition. Okay. Now let's go and build a relational architecture. Suppose we want to build a database system that supports two data models and data languages. What we need here in this case, since we're not selecting a single component, we create a software bus. In this case, we'd like to go and select Quell and SQL. So what we've done is created a software bus that supports both Quell and SQL. Now we have to specify how we implement links. Suppose we want to implement them like DB2, meaning that we want to use both nested loop and merge join algorithms. So we create a software bus, we select nested loop and merge join, place that on the bus. And the storage system that we just created was db2.ss. So we go and select storage system, db2.ss. Okay, so our database system will support both quell and SQL, implement links using merge join and nested loop algorithms, and store conceptual relations using the db2 storage system that we defined earlier. Let's go and save that. All right. Now we're going to create a database system. The architecture that we just built, we click onto this bus, db2.arch. Now when we're processing queries, we need a set of operations, stream operators, of which will include cross-product, L-filter, and sort. If we don't include them, there will be certain operations that we won't be able to process. Then the data type bus lists all of the primitive data types that we'd like to have our database system support. Integers, C strings, and double would be useful here. Now suppose we decide we don't want double, what we can do is we can just go and remove it. So editing these designs is quite straightforward. Finally, we have to go and select our recovery module. It's currently set to be before image, but we could select no recovery or shadowing, and I'll stay with before image. So that's our specification. What we'd like to do now is to go and generate a transcript of what we've defined. We're going to save that in a special directory called syslib. And we'll call the name of our system demo. Now these files here, these 4 files, FIT through OPT, these are dispatch tables that tell us which module sits or which component sits on top of each other. If we were to compile the system directly, here are the header files that we would use in the compilation process. Now the size of the system we're generating is approximately 32,000 lines. It's actually a bit more than that because of some header files that we're not including in this estimate. We're using approximately 50% of the Genesis library. And it's very easy to go scale up this type of technology just by adding more components to the target system. So let's leave the editor. Okay. Now the system library, these are the dispatch tables, which we're just going to drag into a special folder called genconfig. All right. Now let me show you a schema. From this point on, we're ready to run. Here's a schema, the Atlas schema. The Atlas database consists of 3 relations. This is an example database that we're going to use just to test the database system that we just created. The Atlas database consists of 3 relations. Nation is a relation of tuples that describes individual countries, using their name, capital, and so on. Border contains tuples that describes which countries share common borders. Invent contains tuples about different inventions, like the name of the invention, the name of inventors, and the country where the invention was created. The Atlas database also has 2 links. Links are defined by a name, like invented here or invented in, followed by a joint predicate, which in the case of invented in link tells how nation tuples are going to be connected or related to invent tuples. DDL commands are conveyed in the schema using tags which adorn links, fields, and relation definitions. If we wanted to implement links using pointer arrays, we use the pointer array tag. If we wanted to use ring lists, we'd end up using the ring list tag. Since we don't support these two implementations in our current database, I've commented these tags out. However, if we go and take a look at nation code, this attribute, it's tagged with index, means that we're going to create an index for this particular field, and nation code also is the primary key of this relation. So again, this is a quick overview of just some garden variety database, which we'll call Atlas. And now what we want to do is compile this schema and then load the Atlas database to query its contents. So the two executables that we have are gdefine, which compiles this schema, what it's doing, it's listing all the internal relations that was created in the conceptual to internal mappings. And then we run gdml. This executable loads the database and presents us our query front end. What we're doing now, it sees that the database wasn't loaded, it's going into some raw data files and loading the database. Each record that you see, we're actually printing out every 100th record. Okay, remember our database system presents us both with an SQL and a quell interface. We've gotten the quell prompt, so if we say select star from invent, where year equals 1868, we get 3 tuples. We could have requested the same set of relations, or tuples, by expressing it in quell. So now we get the quell prompt. We say range of I is invent, retrieve, year, 1868, and again, we get the same result. Now we support, again, subsets of quell and SQL that you can do retrievals, joins, insertions, deletions, the standard set of operations that one would expect. And I won't illustrate this aspect further. Again, you're basically dealing with a standard database. What we were doing is actually running the database system that we had just defined. Let me again give you a recap of what we've just done in the last 10 minutes. What I did was specify the design of a customized database management system. I used the Genesis layout editor to define the series of components that defines the target system that we were interested in. I then generated an internal transcript, which is essentially a set of dispatch tables, and copied them into a special directory off of which a particular version of Genesis was used to actually go and run the executable, target executable. I then showed you a simple database. I compiled it and then loaded that database and then ran some queries. Again, all within a very short space of time. The power and potential of this approach really lies in large-scale reuse. I know of no comparable technology in the database area that can achieve all of this in this time frame. There are a number of projects that are currently underway to extend Genesis. Currently what we're doing is adding inheritance building blocks or components that give you the following options. You can support multiple inheritance or single inheritance. There's a variety of different implementations that we're providing, and also you can choose among different conflict resolution algorithms. We are also implementing client-server components. Our goal is that we want to be able to build distributed database management systems from components just as we're doing with centralized database systems. And we are also developing a technology by which we can go and customize object-oriented DMLs. What we're doing is trying to apply Genesis technology to the realm of data languages. We want to be able to synthesize customized object-oriented data manipulation languages very quickly from a very simple set of specifications. We're also continuing to extend Genesis on the front of software development. The very simple formalism and paradigm that I presented earlier unifies the results of domains that have nothing to do with database management. For example, the communication software counterpart of Genesis is Avoca, a project that was created by Sean O'Malley at the University of Arizona. He's building complex protocol suites by composing together primitive protocols. The corresponding version of Genesis in the domain of operating systems is Choices, a project headed by Roy Campbell. And of course, we've taken a look at very briefly at the domain of Unix, where our formalism encapsulates notions of Unix file filters. If you're interested in getting a copy of Genesis, it's available for distribution. The distribution fee is about $140. Please contact me at this address or give me a call at this phone number for more information. Thank you very much.